In this video, I'm going to show you how to turn an idea into reality. We'll talk about component selection, circuit design, and how I use AI to help make smarter design decisions. The idea. I wanted to create some sort of STEM kit that taps into the power of an ESP32, a capable microcontroller with Wi-Fi and Bluetooth built right in. Think of the ESP32 like a gateway drug into engineering. There's a wide variety of sizes, shapes, and capabilities to choose from, and we'll get into that in a minute. What does it control? So what exactly is this microcontroller going to do? Well, I'm a big fan of LEDs and always have been, and so was my father.
It's because you're afraid of the dark.
I'm, I'm not afraid of the dark. I've got small ones, large ones, red ones, green ones, flat ones, hot ones, and even mini ones. For this project, I decided to go with flat surface mount LEDs. Why? They look cool, I've never worked with them before, and they don't draw a ridiculous amount of current. That means they won't solder themselves off the board without some kind of heatsink. Component selection. We'll be using EasyEDA to design our own schematic and PCB, and I like to use LCSC for sourcing parts. The integration between EasyEDA and LCSC is really smooth. You'll see the C number, that's the reference ID for a component. You can preview 3D models, footprints, and specs right inside EasyEDA. But you can also use components from other suppliers and just find matching footprints. So what's a footprint? The footprint defines the actual solder pad layout. It must match the physical shape of the part. If it doesn't match, it doesn't connect. And if it doesn't connect, it's just not going to work. That's why getting the right footprint is 100% critical. Data sheets. A data sheet is like the user manual for a component. Yes, sometimes they're 18 plus pages long, but don't panic. A lot of that is just performance graphs or examples for different variations of the same chip. Here's what I do. Print the data sheet, highlight the critical info, and store it in a project folder. This way, if I need to swap out a part later, say we're on revision 4, I can just jump off a bridge, pull the old schematic, plug in the new one, and we're on to revision 5. Look for operating voltage, maximum current, example circuits, typical component values, although you might have to calculate a few with some simple formulas. But data sheets are a must-have, and honestly, they just make you feel really cool when you can tell people, yeah, I figured out how all this works by reading this entire 18-page booklet, you know what I'm saying? When you just like highlighted 3 sentences. Power math. For example, our LEDs run at 3.2 volts and draw 150 milliamp at full brightness. If I want 9 of them, that's 1,350 milliamps or 1.35 amps total current. Way too much for the ESP32 to source directly. The ESP32 GPIO pins can usually handle a few hundred milliamp tops. Introducing the Mosfet. To solve that, we use an N-channel Mosfet. Think of a Mosfet as a switch, like this one. But instead of using your fingers to turn the switch on and off, we're going to use the ESP32. Let me explain. We're going to use one of the GPIO pins on the ESP32 to output a PWM signal. If you've been around RC for any length of time, you've heard of a PWM signal. It's typically the signal that comes out of your receiver and tells your servos or ESCs what to do. If you look at the signal on an oscilloscope, you can see that as you move your sticks, the waveform changes. This is fascinating to see because you visually see what's going on in the signal and you finally understand why it's called pulse width modulation. Let's take a look at the average or effective output voltage of a PWM signal. Let's say with sticks in the middle and a reference voltage of 5 volts, typically what most RC servos are running on, your duty cycle is 50% because the signal is high 50% of the time and low 50% of the time, therefore creating an average voltage for the cycle of 2.5 volts. Adjusting the position of the stick will adjust the duty cycle and therefore the effective output voltage of the PWM signal. Now, back to the Mosfet. The Mosfet has something called a gate threshold voltage. or VGS-TH. That's the voltage needed at the gate pin to turn the MOSFET on. In the data sheet, we can see that number is 0.8 volts, roughly. So when we apply more than 0.8 volts to the MOSFET's gate pin, which with our centered sticks example, we're putting out about 2.5 volts, it will begin letting current flow through the drain pin or effectively turn the lights on. If we were to bring our RC sticks all the way down, the PWM duty cycle goes down to 0% and the effective output voltage is 0, the lights go out. Fun fact, every computer ever made is just billions of tiny electrical switches, either on, 1, or off, 0. Still kind of blowing my mind, honestly. This is a 1 and a 0 somehow. Other parts. We'll also need a couple resistors for current limiting and gate control, a USB-C port to deliver 5-volt power, and of course, the right ESP32 board. For this project, I'm using the ESP32 C3 Super Mini. It's cheap, it's small, and it's easy to work with. You can find great pinout diagrams online if the datasheet is a little too overwhelming. Now let's build the circuit. Now that we've selected all our components, it's time to jump into EasyEDA and build the actual circuit schematic. Let's get started. Hey, real quick, make sure you use the link in the description below to get up to $60 in coupons for your first orders on JLCPCB. Log in or register if you haven't, and decide whether you want to design online or download. I personally design online because I use multiple computers and I use the Pro version. The standard version does allow you to export more file types for your project. If you'll be sharing your projects, I recommend using the standard version. This is recent news to me, so all my projects going forward will be in standard EDA. For this tutorial, we'll stick with the Pro version, what I know. On the left, after you log in, you'll want to click on All Projects, right-click on your username, and select Create New Project. You'll be presented with a PCB file and a schematic file. Double-click the schematic file, and now we can start building our circuit. Let's insert the LED first. We know that the LEDs have this LCSC number because we sourced it from there. So let's open up the Place Component window and simply paste the C number in the search bar and hit Enter. It should be the very first one. Select Place and click 9 times for 9 LEDs. Keeping your circuit organized is key to continuing to understand it. I learned that very quickly. So make sure to use these distribute and align tools to your advantage. Our next component is the Mosfet with this C number. Paste, place, boom. 3 times. And finally, we need the ESP32. This one can be tricky because I couldn't find it on LCSC. But search that name everywhere, and in the component window itself, if you change up the search parameters, you may just have one show up. And for this, really, I just need a placeholder because I'm going to be using female pin headers, but I do need them to be spaced apart properly. We can verify this once we get building the PCB. Place it, and now we need some expertise to finish it. By this point, we already have a conversation with ChatGPT. That helped us decide what MOSFET to use and even helped decide on the microcontroller. So let's fire it up again to ask exactly what this circuit needs to be completed. It's important to be as thorough as possible to ensure you get an accurate answer. So based on what ChatGPT said, we're going to be using 220 ohm resistors and 10K ohm resistors. Now I'm using these resistors because that's what I have on hand, but you can select pretty much any shape, size, or whatever, as long as it's those values. Now we have to put a 220 ohm resistor in front of each LED. Now let's add a 5-volt connection before each resistor for each LED. Don't forget to keep it neat. a 220 ohm resistor between the PWM signal coming out of the ESP32 and the gate pin of the Mosfet. We'll add a ground connection to each Mosfet. And while you can do this the way that I'm doing it with each individual circuit, the better way to do it would be to build one and then copy paste it twice. The 10K ohm resistor is going to go between the gate pin of the MOSFET and the drain pin or ground. Then it's just a matter of making all the connections. So remember, we're going to be doing 3 LEDs in series, which means each ground of the LED will go to the source pin on the MOSFET, and 3 of those will be connected to that source pin. We do that again for the next 3, and then finally for the last 3. This will allow 3 PWM signals to control the 9 LEDs, with each PWM controlling 3. Now we need to connect the gate pins to the actual ESP32. And the way we're going to do that is with these net pots. And you should think of these as like portals or cables, basically, but it doesn't actually show you the cable. So these net pots are very important that you name them properly to stay organized, but also for the connections to be correct. So to avoid any problems, I actually like to copy and paste them. That way there's no way that you can do a typo and mess everything up. So now we go to our handy dandy pinout diagram to find out where these connections are going to go to generate a proper PWM signal. Pin 9, 10, and 11 look like good candidates. Now, the last component we have to add to our circuit is the power source. So I decided on this USB-C port with through-hole pin connections. Now, there's a big reason for the through-hole on this. I have tried soldering surface mount USB connections and have had a terrible time soldering it and getting good solid connections. So whenever you can, I would recommend going with through-hole pin connections for a USB. As always, copy, paste, and place, and then we'll start working on the connections. Now, the only ones we're really concerned about here are V-bus and ground. So we're going to go ahead and add the 5 volts and the ground to ground. However, EasyEDA does not like it when you leave pins unconnected. So for CC1 and CC2 and EP, we'll put these little X's here, letting the program know that we're purposely leaving them unconnected. And at this point, we're done with our circuit schematic. Now we can move on to the fun part, actually designing the PCB. Now, since this PCB is going to sit inside of a 3D printed housing, let's go look at that real quick before we get into the PCB. My program of choice for CAD modeling is Fusion 360, and I've modeled up this little logo case that will house the PCB, and I have also modeled the PCB itself in a simple body. And that is the outline that we're looking at. So here we have just a simple outline and then 3 holes for mounting. Now what we're going to do is we're going to export a DXF file of this sketch. So first things first, let's create a sketch, project everything on that. Okay, finish. And it is symmetrical, so it would be easy. You can do it either way, but do keep in mind that you're going to need that's going to be important if your design is not symmetrical and you can't use either side. So you go to Sketches, Export DXF.
and then let's hop back into EasyEDA. And what we're going to do is we are going to click on this little button here, which says Update Convert Schematic to PCB, or you can press Alt-I. It's going to give you this prompt of all the changes, which is basically everything. Connect. Click Apply Changes. And here are all your components at this point now. So now we just need the PCB outline, which we just exported. So we're going to File, Import, DXF. We've got that. And then we're going to import it to the board outline layer. So that's purple. And then just click it anywhere you like. So now we've got the outline of our PCB. And one way you can really quickly check is if you click on the 3D button there, you'll see that's your PCB, right, with all of its components elsewhere. Now it's just a matter of putting the components on the PCB, routing them together, making all the connections, and then you're pretty much done. So let's get to it. The first thing you want to place, or the first thing I like to place, is the actual ESP32. And it's a little too big to kind of place here. It kind of interferes with the screw and other things. So we're going to have to twist it around a little bit. And in order to do that, you come over here and you click on rotation, and you can rotate it. First of all, we're going to rotate it 180 degrees so that the USB port is facing out, or down towards the bottom. Then we'll slowly increase to maybe 190, a little bit more. Maybe you want to line it up with this edge here. Try 200, 220, 210, 215, and maybe 211. That looks good. And so we only really need the connections to be on the board. So here it peaks out a little bit, and that's okay, as long as you take that into account on your design, and we'll get to that. And so we'll just place it there for now. And so you see, it gives you these lines that tell you exactly where everything connects to. So we can start with putting the resistors. And the nice thing is, it's really hard to mess it up at this point. If your schematic is solid, there's really no way you can mess this up. It will not let you connect something wrong, unless you connected it wrong in your schematics, at which point you'd have to go modify that. I like to put all the resistors close together, just to kind of get them out of the way. And then we'll start deciding on where the LEDs will go. And remember, the LEDs will go on the other side of this board. So, a few more resistors. Okay, and then finally, we could put this guy down here in the bottom. It's going to go somewhere down here in the center. Now for the LEDs, I would select them all and then come over here and select bottom layer. So now they're all basically on the other side of this board. And also, if you select one, you want to know which one exactly you're looking at, just go ahead and select one of them, go back to your schematic, and it'll highlight it for you. LED 1 is this one. So you know that's going to go to PWM1. Not super important in this case, but it could be useful if you're working on something bigger with a lot more components. So LED 1 will make one thing we do want to make sure of is that each group is on either on the left or right wing or in the center, right? So we're going to be controlling the middle, the left, and the right. You could also make the top, middle, and bottom if you wanted to, but for our case, that would work best. So You just come back here, you can see LED 1, 2, and 3 are all routed to PWM1. And then 4, 5, and 6 are routed to PWM2. And 7, 8, 9 are routed to PWM3. So LED 1, 2, 3, 4. This one we can probably flip like that. 4, 5, and 6. 7. 8. And 9. You do want to make sure that none of these holes, these will be holes on the PCB to solder the female headers. You want to make sure that those are not lined up with any LED. Finally, Q1, Q2, and Q3, these are our 3 MOSFETs, and we can make sure Q1 is with 1 through 3, Q2 is 4 through 6, and Q3 is 7 to 9. So ideally, you want to kind of place those closer to those LEDs. Come to think of it now, the resistors may have been a better idea to just weight it on those. At this point, you can kind of place them wherever you like. And then change as necessary. Come back here. 1, 2, 3, 4, 5, and 6, 7, 8, and 9. Those are all going to be with the LEDs. So you want to keep those close to the LEDs. Let's look for 1. This one will go up here. And by the way, you flip components around by simply pressing the spacebar. It'll flip them in 90-degree increments. That looks pretty good. Now we check the next set of resistors. The 10, 11, and 12, those are 220 ohm to the ESP32 to the MOSFETs. So with that in mind, we'll try to find the best position for that. You can arrange these in whatever order you like. I try to arrange it in a way where it makes a little bit of sense and it makes routing a little bit easier. You can kind of see the web of connections here that you're going to have to unravel here soon. So you may have noticed how I've been trying to move this LED and I keep grabbing the PCB, and that's because we're working on the top layer. So if we go over here and click on bottom layer, the first thing I'll be able to grab is the actual LED. Go back to layer, top side. If things get a little too complicated, you could always hide the bottom layer and you'll see just the documentation, positive and negative, that sort of thing, which you can also hide. So now 14 or 13, 14, and 15, these must be the 10K ohm resistors that go in between the MOSFET and the ground. And once your layout looks good to you, you can start routing your connections. To do that, we're going to click on this little button here, single routing. You could actually also go ahead and go to route and then auto routing. Click run, and it will automatically route everything for you. But I've heard this isn't the best way to do things, actually. So we'll go to single routing, and I like to work in millimeters, not mil, because I don't know what a mil is, to be honest with you. And there's probably a rule of thumb that you can look up for how much current is going through a track, but for our application, I think 0.254 will probably be okay. So one thing I want to mention early on is don't worry about the ground connections, because what we're going to do at the end is we're going to pour a ground layer, or pour a ground copper layer, which is basically going to fill in all the spots that don't have routing on it, and that's going to be our ground plane. So we can start with PWM1 going to this resistor. And it's very easy because it really does not let you mess it up. Like you see, as soon as you click on a spot, it only shows you where it connects to next. It doesn't allow you to connect it to anything else, and it'll just kind of bounce around it. So that's a ground. We don't need to worry about that one. You see how that one connects to multiple things? Now here we go from the top layer to the bottom layer. Now, how are we going to do that? Well, there's one easy way to do it, and that is to just kind of click on your way there, click somewhere there, like right about here. And then we're going to just go to layer and then go to bottom layer. And it's going to automatically create a via for you, which is basically a conductive hole that will connect the top to the bottom layer at this spot. And then boom. You do want to keep the routing as straight as possible and avoid as many curves as you can. And now for the LEDs, since you're going to be, since the MOSFET switches the ground side, it disconnects and connects the ground side, you do have to actually connect the ground part. And that is actually what we did right now. This would be the positive side of things, I believe. And honestly, it doesn't even matter. Once again, this is a top layer. And so yeah, you just kind of keep working your way all the way around. Now at the end, all that you should be left with is ground connections. So now if we look at our 3D model, you can see that everything is in place now. And that's what it would look like. And those are the LEDs on the backside. But you'll notice that this doesn't look like a professional PCB, in my opinion. This routing is all very singular. Usually there's much more going on in a board, and we can do that. And remember, we haven't done the ground connections yet. So to do the ground connection and to make the board look better, in my opinion, you click on this dashed line copper area icon, and then you create a box around the entire thing. And what you're going to do is you're going to make sure that the net pot is the ground pot. So this is just going to create a copper pour over the entire PCB that's connected to ground. Just click confirm, and this is on the top layer, although we will be doing it on the bottom layer as well. And now you can see how the routes are closely joined by these by the copper pour that we just did. And you'll notice also that all the remaining connections are done. and go to the bottom layer, and we'll do another pour. Ground, bottom layer, confirm. And so now we've got the copper pour on the top and bottom layer. So if we look at the 3D model now, it looks just a little bit better. And at this point, you've pretty much got a working PCB, but there's a couple more house cleaning items that we got to do. The holes here, you'll notice they're not actually holes. And then also you might want to add some text on this to, make it your own. So to make these holes actual holes, what you need to do, or what I've been doing, is using this pad. And so you just try to get that right in the center there, and then you change the dimension of whatever that might be. And before you do that, actually go ahead and delete that ring to make things a little easier. So the diameter, the nice part about this is that it gives you the hole diameter and then the diameter of the metal plating around the hole. So let's say we're going to put 3mm screws in through there. Let's do, although that might be a bit much. Let's do 2mm screws. So let's do 3mm diameter with a 2.5mm hole. And now you've got a hole like that. And now you'll notice also that it's encroaching on the copper pour that we did. So if you need to redo the copper pour, you can just click anywhere on it and then put rebuild copper region. And you'll see it'll give it a bit more space. And you will have to do that for the bottom side as well. Now what I like to do to make all your holes look exactly the same, you just copy and paste them. So you'll notice here you got a little X. That's a little too close to that 5-volt rail probably. Let's keep going though. We'll fix that in a minute. Rebuild the copper region first on both sides. And now we're going to take care of these little X's. This is that. This is why you had to delete the outline layer before you did this. And delete that. So now the only thing we really have to fix is that 5-volt rail on the top side, which we can do by simply scooting it over and then rebuilding the copper region. That looks pretty good. So now if we look at our 3D model, we've actually got holes where we can mount this PCB on to something. Now you'll notice that the actual ESP32 is on here, but remember we're just going to be using the holes that it produced for us to create a female header, so you can actually remove the chip if you need to. Now let's add some text on there to make it our own. But anyhow, let's get the Lloyd Industries logo on here. So one thing we could do is you can import an image, and we've got that. So it's obviously pretty big. Let's go to the top layer. Just place it. We can change the height, and we can link or unlink the width and height so that it scales proportionately. And we'll go with a height of maybe 5mm, see how that works for us. That's a little too big still. Let's go with 3, 2. Maybe that'll work. Not really. 1. That's better. And let's go with 1.5. And then also we'll have to rotate it about, I don't know, 75 degrees. maybe 70 degrees. And we'll bring it on to here. It's still too big. Jeez. Okay. And you'll notice that it's red on red, and that's because it's just a top layer. But if we go to top silk screen layer, it turns to yellow. And now that will be printed in the same way that all these little designators are printed. So if we look at the 3D design, you've got your text. And of course, you can change this to whatever color you like. Green, white is actually one of my favorites. Black, purple even. And you could add text, just normal text if you wanted to here, and they've got a selection of fonts for you to pick. This is an example. And we can just click that right there, and you can change the font after the fact to different things. Like I used to use this quite a bit. And once again, it's on the top layer. Let's bring it to the top silk screen layer, or you can make it the bottom silk screen layer and it'll automatically mirror it for you. And we can place it here, for example. And now when you go to the 3D view, there it is. So when you're happy with your PCB with all your designators and text, pictures and whatnot, one thing you can do is actually export this as a object or a step file, and you can have it, and you can open this up in CAD, and you'll be able to see, and you'll be able to replace this with an actual CAD file of your PCB. So let's do that. Insert its current design. Hide your PCB, and you can actually see if it would fit inside there as expected. It looks like it would. Holes are lined up, and the USB-C port is not perfect, but you can keep adjusting that either in the CAD file or in the PCB. Or if you're interested in learning how to use CAD software like Fusion 360, I will be making a video shortly on how you can design this exact piece. And this should teach you the fundamentals of using pretty much any CAD software, really. When you've done all that and you've looked at your 3D design in awe for hours, then you can go ahead and select this button here, which is PCB fabrication file or the Gerber file. Name it whatever you like. Export the Gerber. One thing you should do actually before you export is check the DRC. DRC is a design rule check, so it's going to make sure that everything is connected properly and that there is no errors with certain things. And now if it passed, you'll just see the download window, which is good. And then you can save it as whatever you like. You could also export the bill of materials and the pick and place file, which is going to allow you to have JLCPCB manufacture and assemble this for you. Those are the two files that you'll need for that. And if we go to JLCPCB, new website, nice. If you go to JLCPCB, you'll find that where it says add Gerber file. Upload your Gerber file that you just exported. And you'll have an instant quote. Now, a couple of things with all the options here. Might seem a little overwhelming, but let's walk through them real quick. FR4 is the most typical PCB material, which is basically, from my understanding, a kind of fiberglass material. There's also flex, aluminum, copper core, whatever Rogers is, and PTFE Teflon. And it actually gives you a nice description of what all of these things are. But for me, I typically go with FR4 unless you need some special application for this. Layers, there's two layers, the top and the bottom. You can go up to 4, all the way up to 32, which is wild. The dimensions you don't have to worry about. The dimensions are in the PCB itself. Quantity, the minimum order quantity is 5, which is good in case you blow one up. Product type, I just leave that industrial consumer electronics. Different design, click 1. Delivery format, single PCB. So single PCB. PCB thickness 1.6 is the standard, I believe. PCB color, this is where you get to pick what it is. And green is usually the fastest one to turn around. The other colors might take a little bit longer just because they tend to batch them together with other orders, and green is just the most common. Although I think we should always order something else to get those to be a faster turnaround. And the silk screen color does change. If you select blue, for example, that'll stay white, but if you select white, it'll be black. Material, FR4. Now surface finish, the only reason I changed this one is because it says with lead, and I'd prefer to have lead-free stuff, especially with the little ones running around. So I select lead-free HASL, which does increase the price just a little bit. You can see here it goes from 610 to 730. Worth it in my opinion, in case one of my kids decides to swallow one of these. Copper weight, I always leave it at 1 ounce. Via covering, tented, untented, plugged, epoxy filled, and capped. So these are about the holes that connect one side of the PCB to the other, and it's super easy. It explains everything to you right there. And then everything else, for the most part, I kind of leave alone, unless you are doing a PCB assembly, in which case you can toggle that on and it will ask for more information on the later steps. And then one thing you can do to make your life easier when you're soldering this is order a stencil. And I would go with a custom size, otherwise it's pretty big. But a stencil is basically just a thin metal sheet that's going to have holes right where all the solder paste needs to be, so you can align it right on top of your PCB, and then just smear on some solder paste, and the solder paste should stay on, or should go through the holes and stay on to the board where you actually need the solder, and it'll be the perfect amount of solder. That in itself requires a bit of skill, but with components like this, I think it's pretty easy to just solder or place the solder paste yourself. It's very forgiving. And then once you've got that, you're pretty much ready to go, and you're spending $7.30 for 5 of these, which is pretty amazing. Now, the shipping fortunately does cost a little bit more than the product, but still $30 for a custom PCB, I think is pretty incredible.
If you're still here, congratulations. You have more patience than most people I know. Please use the code ICANDOIT on checkout to receive $5 off the PCB stem kit. You can order it on lloydindustries.store. The kit comes with 2 PCBs, one ready to plug in and the other bare, ready for you to practice your SMD soldering skills. It also includes all the components required, the 3D printed enclosure, as well as a pre-flashed ESP32C3 Mini. You just power it up, connect to the Wi-Fi, and follow the prompts to configure the device. The only thing you would need is a soldering iron and some solder. Make sure to check out the description for my recommendations on soldering irons and hot plates. Also, a big thanks to JLCPCB for making custom PCBs accessible to everyone, and for sponsoring the channel. On the next videos, I'll be showing you how to design set enclosures on Fusion 360, which should teach you the basics to really let your creativity run wild. I'll also be making a video on how to program the ESP32 in code using ChatGPT or other AI. And I'll also be making a short video on tips and tricks on how to solder onto SMD boards. Say hi, Mom!